Hi, I'm Corey Christous. I'm a software engineer at Confluent, and I'll be presenting AMI creation and infrastructure as code deploys via Semaphore. A quick overview. I'll provide some context for my organization. Then I'll describe the problem that we solved. Following up that, I will describe the approach that we took and some design details. And finally, I'll wrap up. Starting with some organizational context. My company has been using Semaphore for a few years. We migrated to self-hosted agents and server last year. These provided us with more control over the infrastructure, which our organization wanted for security and compliance reasons due to the nature of our product. My team manages the Semaphore infrastructure. Our team, other teams are encouraged to make contributions to the agent infrastructure. In reality, it doesn't happen very often, but it is something that we need to support. And lastly, we are migrating from Jenkins. The majority of our workloads already run on Semaphore, but some older, more complex workflows still run on Jenkins, and that work is in progress. Okay, next I'm going to talk about how we manage our Semaphore agent infrastructure. This is a specific use case related to Semaphore, but the solution could be tailored to other similar problems, and the solution isn't even specific to Semaphore. So we were running our commands for managing our Semaphore agent infrastructure from laptops, and this didn't scale very well. There are lots of create and delete permissions that were required to do so, with non-team members needing them to develop as well, so this wasn't great. People needed to install a bunch of tools on their laptops. We had instructions documented, but it was extra overhead for new contributors. We have 7 different AMIs at this point, which could need to be built in parallel, and all these builds need to maintain persistent connections during their creation. So this could end up taking a long time or have a lot of parallel processes running on your laptop. We have many different environments as well: pre-production, production, self-hosted server, SaaS server for each AMI with multiple sizes. Overall, we currently have 36 agent pools, which is a lot. The steps for performing every action related to the infrastructure were pretty complicated, and it was error prone. So we didn't want to cause any more problems for our users. Changes to the shared infrastructure were also made prior to review, and combined with complicated steps, this was leading to breakages in some cases. Okay, next I'm going to talk about our tech stack. So we're using Packer for creating our AMIs. Originally, this was copied from Agent AWS Stack, which I'm going to talk about in a moment, but since has been adapted to our use case. Our AMIs now contain software that Confluent requires so that it doesn't need to be installed during job executions. And you may be asking, what is an AMI? An AMI is an Amazon machine image. It is essentially a configuration for setting up an EC2 instance. And what is AMI creation? It is creating an EC2 instance, installing some software, saving that as an image, and sharing it with our organization so that we can use it later. The Agent AWS Stack is a CDK application used to deploy a fleet of Semaphore agents in an AWS account. This is provided by rendered text. It's open source. CDK is an Amazon-specific infrastructure as code tool similar to Terraform. And Agent AWS Stack has various configuration parameters that suit our needs. So it's great that rendered text could provide it for us. And Terraform is an infrastructure as code tool as well. We use this only for managing our alarms and our dashboards. I think in most cases, ideally, we'd only have one infrastructure as code tool. However, in this case, it's a nice clean line of responsibilities. Rendered text maintains the core infrastructure to run our Semaphore agents, and my team maintains the monitoring infrastructure, which is tailored to our needs. Okay, next I'm going to talk about how we approached our problem. So these are the tenets that we followed while building our solution. We wanted to automate the solution to save everyone time so we can spend our time working on more important things. We wanted to experience the same development workflow as our customers so that we can better serve them. And in some ways, our use case is more advanced, so it gives us a deeper understanding of our product offering. We also wanted to reduce the likelihood of outages for our customers so we could keep them happy. Okay, next I'm going to talk about the solution. Note that for this solution, it is a closed source repo, so I won't be able to provide you with a link to it, but I will show you some code that is particularly noteworthy. So we built a Semaphore pipeline to deploy their Semaphore agents. I don't expect you to be able to read this page, but it's a high-level view of our pipeline and one of the branches through it. The main thing to note here is that there's 3 different stages in this pipeline in different columns. So the first column, we build our AMIs. The second and third columns, we deploy to pre-production. And the final 2 columns, we deploy to production. Okay, then getting into the AMI creation. The creation process typically takes between 30 and 60 minutes, depending upon which OS we're building. You can see here that one of these only took 15 seconds. This is because we have a hashing mechanism in place, which prevents rebuilds of identical artifacts. The build AMI sh script does all the steps to create AMIs during, including the hashing. The hashing is done by generating an MD5 of sorted MD5s, and then this hash is put into the AMI name. And before we create a new AMI, we check the name to see if it already exists. If it already exists, we don't rebuild a new one. We just use the existing one. Also noteworthy here is that we have conditional runs. So we only build AMIs when there are changes to the source related to them. So when we make a change to a Ubuntu AMI source, the pipeline doesn't also build the macOS AMIs. Also, I wanted to mention that we pin some of the tools in our AMIs. So we generally pin tools in our AMIs that we expect our users to use directly. So we aren't pinning things like GCC or like compilers, or but we are pinning things like JQ or Docker. There is a maintenance trade-off, because if we pinned everything, then we'd constantly be updating versions of tools as bugs are found or vulnerabilities are found. And we found this was a happy medium for us, at least at this point. As an example, we recently rolled out a new image, and it caused issues for some of our use cases because of a Docker bug, which was introduced by a new major version, and we resolved this by pinning Docker. Okay, next I'm going to talk about the pipeline promotions. At the top, you can see here what a non-prod promotion looks like in our pipeline. Below, you can see the differences between the non-prod and prod promotions in the pipeline configuration. The non-prod is an automatic deployment on the master branch when the relevant files change. And then the prod is a manual one. And this is important because it gives us extra control exactly when we want the prod deploys to happen. So for example, we might not want it to happen on a weekend or a nighttime or Friday or whatever it may be. We can make the decision, what is the amount of risk that we're willing to take based upon the time that it is. Also, for PRs, we run the same pipeline for our PRs, and they create AMIs if the related source changes. This is especially useful for concurrently changing multiple AMIs. So a user can make a pull request, and it will generate the AMIs for all of the different OSs, and that will make it easy for them to manage. They never auto deploy to prod, non-prod. The pipelines never auto deploy to non-prod. Users can manually deploy to non-prod via the Semaphore pipeline if they need to. The non-prod environment is a shared environment, so that there is potential for conflicts. However, for this repo, there's a low change count, and the testing is typically pretty quick, so we don't typically run into contention. When we do create PRs, we create them as drafts, GitHub drafts. So repo owners don't get extra GitHub notifications. And then once testing is complete, we convert them from drafts, and then that opens it up for general review. Deploys are first an infrastructure update, followed by a test, which is a dependent block. So the infrastructure is deployed in the same way that software typically is. So we are truly treating infrastructure as code in this case. You could see the changes flowing through the environments of the pipeline with gates in between. Deploy sh is very similar to build AMI sh in handling. I'll show you some of the details of that in the next slide. In the test block, you can see that it runs on the agent that was just deployed. So we do a deploy for macOS, and then we run the test on a macOS agent. And the test just runs a shell script, and at this point, the testing is pretty remedial, but it importantly tests the agents still connect properly with the server, and they can actually run jobs and report results, or sort of the basic fundamentals. This block also could check metrics if we wanted to. Maybe that's something we'll do in the future. So deploy SH has 3 noteworthy steps. First, we deploy agent AWS stack. We set an environment variable with the path to the file that contains the parameters, and then we run the deploy. Then afterwards, we disable all of the idle agents. The agent AWS stack deploy only tells the auto-scaling group to use the new AMI for new instances. All of our agent pools are configured to terminate agent hosts after job completion. So this step ensures that the test job will run against a new host using the latest AMI. So this design leaves us with all of our existing running jobs unaffected during the deployment period. Only the new jobs that start immediately after the deploy finishes will be using the new AMI. Lastly, we deploy our Terraform resources. When we go to production for a given AMI, there may be multiple pools of varying sizes. In this case, we have 5 production pools for the AMI associated with a single Semaphore server. All right, so wrapping up, we now run the pipeline, and we have improvements in these areas. For permissions and laptop setup, they are only needed for cases where bad AMIs are deployed that break all pipelines. Because we deploy Semaphore agents using Semaphore agents, we can get into a locked state where a broken agent prevents us from deploying. This doesn't happen very often, but in this scenario, we can fix this from our laptops. All AMIs are built in parallel, so we don't need to maintain persistent connections from our laptops, and things get done generally much quicker with lower overhead. Changes to the pre-production are automatically verified before going to production. This gives us more confidence before making changes that could affect our customers. The steps are now pretty easy. We just create a pull request, and then you wait for the results. And since PRs are now the easiest way to test, all changes go through PRs prior to being made to production. We could improve the testing of our AMIs. It could be more thorough with more permutations and cover more use cases. So this would help us from preventing regressions going to production. And after we did so, we could enable auto deploy to production once we have that confidence from the testing. We also could use ephemeral non-production pools as the pipeline executes. This will reduce our static costs associated with these shared environments as it is now, and alleviate the need for the problem with resource contention. But this work might not have high ROI. We'll see about this in the future as things progress. And that's all I have. Thank you for your time.